Hello and welcome to Eng Phys 2P04 Lecture 22, Thermal Expansion. Here's what we're going to be doing today. We're going to consider that when materials heat up, they expand. This happens in the absence of stress. So the strain that comes just from the temperature change is the thermal expansion coefficient, alpha, times the change in temperature. Alpha usually has numbers around 1 part per million per Kelvin, and since a Kelvin is equal to a degree Celsius in terms of the difference from 1 degree to the next, then you can just use a change in degrees Celsius without having to convert to kelvins. Okay, now this is a new source of strain. This shows up because when a material is heated, there's more energy per degree of freedom inside the molecules of the material, and since they have more energy, they're bumping around faster. They tend to jostle each other and end up with a larger space between them. Imagine there's like a group of people that are trying to cluster together. If they're all holding pretty still, they'll be able to cluster really close together. But if they're trying to cluster together while at the same time trying to run as fast as they can, then on average they're going to be smashing each other apart and being okay with a farther away separation distance. And there's your analogy for today. That's why thermal expansion happens. Okay, now the thermal strain, the fact that we have this means that we have to distinguish between the two types of strain that we've been dealing with so far. If you think about it, we've used two definitions of strain. We've used the idea that strain is the change in length per unit length, or the derivative of the length change in each direction with respect to the distance in that direction. So del change in x per x, change in position in the x direction per unit x, that is. So the change in length per unit length. And the other definition was that it's the stress divided by the Young's modulus, or the stress divided by stiffness more generally. So to distinguish between these two types of strain, we're going to call this one the physical strain. So the length change per unit length is the physical strain, or the true strain. It's the actual strain that shows up, the actual change in length per unit length. And we're going to call this one the stress divided by stiffness. We're going to call that one the mechanical strain. That's not a term you'll see elsewhere. I made that up. So if you see mechanical strain somewhere else, then maybe somebody else had the same idea as me, or maybe I subconsciously got it somewhere and didn't even realize. But anyway, this is you're free to use this and popularize that term. I'm happy with that. Anyway, there's there's really a difference between these types of strains. Call it whatever you like. There's the change in length per unit length, the stress per stiffness, and the thermal expansion strain. Okay, let's look at some extreme cases to try and get a feel for how this works. Suppose the bar is free, then there's no stress, and then we've got that the change in length per unit length is just alpha delta T. Now if the bar is fixed, it can't expand, then increasing the temperature causes a stress to show up in the material instead. What kind of stress? Well, if you raise the temperature and it tries to expand but it can't, then you'll find the stress is negative, means it's in compression. That makes sense. We're holding it together. We're holding it in this smaller shape, smaller size, to prevent the thermal expansion. Constant temperature is the case we were dealing with before. If there's no temperature change, then the change in length per unit length is just the stress divided by the Young's modulus. All right, well, how can we change FlexPDE to account for this new thermal strain? Previously, here's what we were doing in FlexPDE. We had the strain definitions in terms of the change in length per unit length for both axial and shear. We had Hooke's law defining the stress in terms of the stiffness times the strain. And we had the continuity equation saying that the stress has to be continuous over the interior of the object. This also gave us the ability to set up stress boundary conditions as loads. How can we modify these to account for the possibility of thermal strain? So let's look at what each of these say. First one, strain is the change in length per unit length. Okay, well that's still true of the true strain or the physical strain. The next one says stress is the stiffness multiplied by the strain. And the third one says stress is continuous. Well, stress is still continuous, but let's look at this interior equation here. Stress is not the stiffness multiplied by the physical strain, it's the stiffness multiplied by the mechanical strain as we defined up here, right? So this is where stress now isn't necessarily equal to the stiffness times the physical strain. It should be equal to the stiffness times the mechanical strain, where the mechanical strain is then equal to the physical strain minus the thermal strain. So that's what we can do. We can distinguish between physical strain, the one we defined up here, and the mechanical strain being the physical strain minus alpha delta t, giving the possibility of alpha being different in each of the three directions, which it could be for the crystal systems that we're dealing with. Then stress is defined via Hooke's law, but now using the mechanical strains. So we didn't have to deal with shear. It turns out that shear only affects, that temperature change can only cause shear directly in the material if we have a crystal system that's very asymmetrical. So what's called a monoclinic or a triclinic crystal system, and that's a lot less symmetrical than quartz is. Okay, next example. Silicon has a thermal expansion coefficient of about 2.6 microns per meter Kelvin at room temperature. That's another thing. These thermal expansion coefficients, even though we're going to be using them over wide temperature changes to see big strains showing up in FlexPDE, in reality, the thermal expansion is not linear over huge ranges of temperature for most materials, so you'd really have to get some experimental data of what the thermal expansion coefficient is at 0 degrees and at 20 degrees and at 50 degrees and at 80 degrees, and then use the appropriate thermal expansion coefficient over each range, really integrate this. Okay. A MEMS bridge made of silicon has dimensions, so MEMS, micro electromechanical systems, using silicon electrical systems to build mechanical things on the size scale of micro machining, really small things. So it's got some dimensions, 10 microns by 2 microns by 1 micron, and it's fixed to the substrate, so the bulk silicon, on each X face to have zero displacement in any direction. Calculate the stress that results in this cantilever in response to heating up 50 degrees C. Heating up by 50 degrees C is what we're going to interpret this to mean. Okay, so let's, before we solve this with FlexPDE and find out how things are really behaving in response to the anchors, let's use the equations here to come up with some approximate solutions. So to do these approximate solutions, we're going to need some numbers for silicon from the table we had from lecture 20. Which is cited if you go and look back at that lecture. It has the stiffness matrix coefficients for silicon that we're going to need. Silicon is one of these crystal materials, rather cubic crystal materials. So C11 is going to be C22 is C33, and C12 is C13 is C23. So it's got these stiffness coefficients, Young's modulus, Poisson ratio, shear modulus, and asymmetry factor. We're not really going to need the asymmetry factor. So these are the coefficients for silicon that we're going to need. And the first step is to say, well, let's guess that the strain is 0 everywhere. So it can't move in any dimension on the X faces. So since we're holding it on each edge, maybe it doesn't deform at all. It doesn't change its shape along the length, and then that would mean that it can't move in Y or Z anywhere along the length either. This assumption is not really going to be that good for the dimensions because it's pretty long in X, but it's not long in the other, it's not that big in the other dimensions. So this is really going to set up a boundary condition. So first let's solve it under the case of 0 strain. What that means is the mechanical strain is just 0 minus the thermal strain for all of the axes. So rather than being something unknown minus the thermal strain, it's 0 minus the thermal strain. So it's just negative alpha delta t. And then we can say that we've got a stress given by the stiffness multiplied by the negative thermal strain. Substituting in our numbers, we find a stress of about 40 megapascals compression in all of the different axes. So why can't we use E for this? Like why isn't sigma just equal to E times epsilon? Well, because it's fixed in the other axes, so we have to use an effective E, which is a little bit larger, and that's what C11 does. So remember that S11, the compliance matrices 1,1 component is actually equal to 1 over E, but the stiffness matrix is, that's not plural of matrix, that's the possessive of matrix. The stiffness matrix's 1, 1 component is the thing that maps strain over to stress if the other strains are 0, not if the other stresses are 0, as the Young's modulus is for. Okay, that's the first guess. Now the refined guess is to say that since it's quite long in x compared to y or z, we're going to put no stress in the other dimensions rather than no strains in the other dimensions. So that means that we're solving this condition. So here's the mechanical strains. Now, why didn't we substitute in those as the physical strain minus the temperature change? Well, we could have if we actually needed to find the physical strain, but the point of this is to just figure out the stress in x. So we don't really care about those anyway, but we are going to put them in there to show that they're parameters that could change what our answer is. So we do need them only to find out what the stress is. Okay, so solving this with Maple by substituting everything in, we come up with a stress number of about negative 16.9 megapascals. So 16.9 megapascals in compression. Now that's a lot less compressive stress than it was when we constrained all 3 axes. That matches our intuitions, because if we stop it from being able to expand in y and z, then it's going to try to expand more in x, and that's going to mean we'll get more x stress than if we do let it expand in y and z. Okay, now let's check this with FlexPDE. So here's the solution with the anchors, with everything fixed on the edges. And here's the solution with everything fixed in all dimensions, so it can't move in any dimension. On the top surface, it can't move in, well, it can't move outward in that dimension on each dimension. So it can't move in the y direction on the y faces, or the x direction on the x faces, or the z direction on the z faces. And then here's what it looks like if you allow it to move freely in y and z, but fix it in x. So this one matches exactly our extreme case, negative 16.9 megapascals. This one matches exactly our other extreme case, negative 38 megapascals. So these serve as checks of what we found. But then look at what this one is. So here's the actual stress. The average looks like it's around maybe negative 18 or so megapascals. So that does look like it's between the 2 cases. Of the 2, it's certainly much closer to the one where it's free everywhere. But interestingly, near the anchors, the peak stress is actually larger than the stress you would have gotten if it really was constrained absolutely everywhere. So the anchors introduce stress concentration points, which may cause it to cause the beam to break. So almost certainly, if this thing breaks from heating up, it's going to break at the anchors, unless it flexes first and is able to concentrate stress somewhere else. We'll see some flexion in a later lecture. Square plate with a round hole. Suppose you heat up a square plate with a round hole in it. Does the hole get bigger or smaller? Okay, well, intuition says that since every part of it moves farther apart, if it expands uniformly, the hole should actually get bigger, right? So let's see how that works. So here it is in FlexPDE. We haven't constrained the position anywhere, and we've just told it to increase in temperature. And sure enough, the right-hand side moves to the right, the left-hand side moves to the left, and the right side of the hole moves to the right, and the left side of the hole moves to the left, so that means the hole's diameter has increased. Right. You can calculate what this is by looking at the displacement at the right edge minus the displacement at the left edge, and it is a positive number. So since we've got a positive displacement here relative to there, that means the hole's diameter has increased.